today is actually like maybe a third of the way through the lecture today is an inflection point in the course. We actually, we come to the emotional, I would say the bottom, and then we start climbing out. And so later today we'll be talking about problems, and then we're inching our way towards actually things that are actually actionable, things you can actually do and code, and that's coming. And so it's a good point. If you survived this far, that's pretty good. Let me say a little bit more about that. Depending, I mean, you don't need to, but there's absolutely no reason that you couldn't like basically pip install CVXPy now, if you're curious. Because then what you'll see is actually the code is going to mirror actually all of the stuff we've done here. The composition rules, all sorts of things like that. So this is, I mean, depends, but this is not at all a bad time to do that. By next week, you'll need to do it. But it might be sort of fun to actually see the stuff we've been talking about, but now sort of codified in, well, Python in this case. Okay, so it depends on your learning style, but it might help make all of this look more real. Well, it's going to get more real very quickly, right? So let's see, what else was I going to say about that? No, maybe that's it for now. Okay. So, and homework 2, I would just mention is, I believe, the last not fun homework. That's the one you're doing right now, right? So we transition in homework 3 to actually interesting stuff. So just to give you a rough idea, so you're not going to get 10 weeks of homework 1 and homework 2 type things. So we're gonna segue to actually stuff that's interesting and useful and all that kind of stuff. Okay. Any questions? Now, I guess we are literally at the emotional low point of the class. Although I suppose it's not that. I mean, if you've survived, then I guess that's good news. But any questions about where we head from here? Okay. If not, what we'll do is I'm going to finish with 2 more. Useful extensions of the idea of convexity that we're going to use in the sequel. Actually, everything we talk about we'll use in later in the class. And remember that I said that there's a whole industry of people coming up with various extensions of convexity, and there's pseudo-convexity and quasi-convexity and log-convexity. We'll talk about that. All sorts of things, and there's like a whole bunch of these things, and whole books written on them and all that kind of stuff. So we have selected a small subset of these that are actually useful. Quasiconvex, which I talked about last time, is one, and the other one, which is interesting, comes up in a lot of fields, but like especially in statistics, is the idea of log-concave and log-convex functions, and that's what we're going to talk about today first. So what is it? Actually, it's not. It's super duper simple. We just say that a function, which has to be positive, is log-concave if its log is concave. I mean, so that's all it means. Okay, sorry. Log-concave. Now, there's a weird asymmetry here, and it turns out it's log-concave things that come up all the time, not log-convex. So if you do a Google search on like log-concave, you'll get zillions of papers and books and things like that. Log-convex, you'll get almost nothing. So it's just a weird, I don't know the reason for that, but there's a weird asymmetry. So what that means is if you take the Jensen inequality that defines convexity for the log, and then you exponentiate it, then you get this, and it's actually real interesting. It says that a log-concave function, when you evaluate it at a mixture of arguments, right? That's theta x plus 1 minus theta y, then what happens is, now if it were concave, this would simply be bigger than or equal to the weighted arithmetic mean of f of x and f of y, right? That's what it means to be concave. Here, it's actually, this is the weighted geometric mean. That's what people call it. So it's the weighted geometric mean, right? So for example, if theta is a half, it's literally the geometric mean of the 2 values, okay? So, I mean, this is just kind of repeating stuff. So, there's a bunch of examples like, powers. These powers are log-convex if A is negative, and they're log-concave for A being bigger than or equal to 0, right? So That's one. But mostly it comes up in things like probability densities. So there, a good example is here's a normal density on Rn, right? So that's the density of a standard normal random variable. And here, if you take a look at this thing is log concave, right? Let's check that. Well, if I take the log of it, yeah, this is just a constant and it's completely irrelevant for curvature, right? And then over here, you take the log of that and you get a negative quadratic. Sigma is positive definite. So this thing here is going to be concave, and I'm including the minus sign here. Okay? So that's sort of your canonical example of a log. And in fact, people refer, if you have a measure that has a density that's log concave, it's called a log concave measure. Okay? And they're super duper important in lots of different fields. And it comes up in economics, comes up in statistics a lot. And for example, again, this is just a more advanced topic. You don't have to know about it. It's, for example, a very good regularizer. Like if you say, I'm going to fit a distribution to my data and you insist that that distribution be log concave, that's actually a very sensible regularizer. Again, this is just for people who know what I'm talking about, right? Okay. By the way, a ton of common densities are log concave. I actually don't remember which ones, but it's like a long list of probably most, or at least half of all kind of named densities are log concave. And it's not very hard for you to figure out which is which. Okay, so those are some examples. Okay, here's one. This one is not obvious at all. It's going to rely on there's going to be one new thing in this topic, which I'll get to shortly. But this is not obvious at all, right? So here's the cumulative distribution of a standard Gaussian distribution on R, right? So that's the CDF. Now, of course, this function there's libraries that compute this and all that sort of stuff. Obviously. But this is not obvious at all, that this is actually log concave, okay? So there's that's like a homework exercise, and it's not a short one, and it's got hints, okay? So it's not totally obvious, but it's true. Actually, we're going to see later that any CDF of any cumulative distribution function of a log concave density is going to be also log concave, okay? So, okay. So here's some properties. Some are obvious. This just translates, if you write out the formula for what the Hessian of the log of f is, and you say that's less than or equal to 0, in a matrix sense, then you take the x, and you get something that looks like that. And it's actually kind of interesting. What it says is, remember, f is positive. So this says that a positive multiple of the Hessian is less than or equal to, in a matrix sense, the outer product of the gradient. Now that's rank 1. And what this means, and again, this is more advanced and we probably won't need this, but I don't mind saying it. When a matrix is less than or equal to, in a matrix sense, a rank 1 matrix, it says that this thing can have at most one positive eigenvalue. Okay, that's what it says. And it says all the others are going to have to be negative, right? So that's the condition, right? So some things are obvious, like product of log concave functions is log concave. That's obvious, right? Because if I take two log concave functions, I multiply them. Now I take the log. It's just the sum of the logs. So it relies on the deep fact that the sum of two concave functions is concave. Okay, so this one is easy. Now the sum of log concave functions is not always log concave. In fact, someone want to give me a quick example? Using maybe the stuff we just looked at? Sum of two Gaussian densities? Somebody want to? All right, here we go. Here's a, okay. Here's one Gaussian, and here's another one, okay? Right? They're both log concave. If I sum those, what do I get? I get some function that goes up, has a bump, comes back down, goes up again, and down. Okay? Could that be log concave? It could not be, right? Because, well, one way to say it is that is actually, then I could look at it, I could say it's not quasi-concave, for example, right? because it's got a portion where it bends down, right? So that's not log concave. Okay, I'll let you flesh out that example more. And then it turns out there is a kind of non-trivial fact about log concave functions. As far as I know, this wasn't known until 1973, right? Whereas most of the other things we've talked about were known maybe in the 1920s, 30s, or maybe no one really asked the question and it was so simple that had we asked people in the 1920s, they would have known. This, I believe this to not be the case for this. So the rule is this. It says that if you have a function that's log concave in two variables and you integrate out over one, so that's this thing. If you integrate out over one, then the result is log concave. Okay? So that's the integration rule. It's not obvious. It's not simple to prove. I mean, it's not hugely complicated, but it's not simple, right? So, and it's kind of cool. It's relatively recent. By the way, this immediately, well, we'll get to that in a second. There's some examples, but so one tells you that log concavity is preserved under convolution, right? So this is the convolution. And this, by the way, this could be in, wait, so this is convolution, right? And it says that if f and g are log concave, then their convolution is. And so in probability, what this tells you is if I have two random variables, each with a log concave density, right? And I add them, then that distribution is also log concave, okay? So that's what that tells you, okay? Here's one. Here's a super interesting one. If I have a convex set in Rn, and I have a random variable with a log concave density, then if I look at the probability that x plus y is in C, right, that is a log concave function of x, okay? So actually this is already super interesting, right? Because C could be the set it could be the set of values where some product actually works or functions, right? It meets all the specs, right? Then Y actually tells you about the distribution under manufacture of those specifications. Then X is like the target. It's how you actually, in the factory, what you target, right? So I will target, 3 nanometers for this critical dimension, for example, okay? And then what this tells you is if you're targeting this and Y gives you your manufacturing errors, notice when I ask for 3 nanometers, I'm actually going to get, let's say, I don't know, a log, one of these, some distribution that's got that's a log concave. It'll be spread around that. And what this says, this then becomes basically the yield. And we'll talk about that, right? So it says that the yield is log concave. We'll talk about that. But that's already like getting very close to a very serious application, okay? Now, how do you show this? Well, what we do is we just write, I'm just going to write as an integral formula, right? And what I do is I have two things here. P, that's by assumption log concave. And I have this function g of x plus y. And g is a 0, 1 indicator function. It's 1 if you're in C, 0 if you're outside. If I take that's a log concave function because it's a log concave function that basically has value 0 inside the log of that. Has the log of the indicator is 0 inside C and it's minus infinity outside C. That's log concave function, okay? Okay. And if you work out what this integral is, it's that, right? And here, this thing is clearly, it's actually a log concave function precomposed with an affine mapping. And that is going to be also log concave, right? So there you go, something like that. So, okay. And let's talk about this yield function a little bit more, just for fun. So here you go, is we have, X are some nominal parameter values for a product. It's what you intend to manufacture, right? And this is a vector of different things. S is going to be the set of acceptable values, right? So this tells you, if you're designing a circuit, it would tell you, it says if various parameters based on your circuit come out in the right range, it's actually going to work, okay? So that's an example. And then W, which we're going to add to what, this is what we target, and W is this model's random variations that happens under manufacture, right? So that's it. And then this is the yield. And it's a yield as a function of basically the settings you target, right? And so it's pretty clear what you want, right? If I wanted large yield and I had a set here, I mean, the intuition behind this is pretty clear. Here's my set. So everything, it works if you land in there, right? And let's make it simple. Let's assume that the perturbations are Gaussian, right? So what happens is, you tell me what the yield is. What if I set my targets here? And here's Gaussian. There's 1 sigma, 2 sigma. Go ahead. What's the yield for that? Let me just rough it. I don't know, 10%? Which is not very good. Everybody got that? So it make sense? Okay. What if, all right. So that was a poor choice of X. What if I'm right here, and let's say that's the 1 sigma thing. What's the yield if I target there? What is it? Yeah, it's a little bit less than 50, right? If this was a half space, if it was just a half space, it'd be 50%. But you also fail by coming out over here, right? So let's say it's 45%. I'm making that up, right? But that's it. Everybody got this? Okay. Now after these examples, you tell me, what should I target to maximize the yield? I mean, it's kind of obvious.
The middle?
Yeah, the center. Okay. Yeah. So what I should do is set my target here, and then if that's 1 sigma and 2 sigma, I'm going to have a very happy yield there, right? Like going to be 90% or 95 or something like that, right? Everybody got this? So this is in 2D, and what this says is this goes down in 10. The exact same problem is you could do this in 10 dimensions, right, or something like that. Okay. By the way, you said the center of the set. And what's interesting is that's something we're going to look at later in the class. But it turns out there's a ton of different definitions of the center of a set, right? Which we'll get to later. Actually, we may see one later today. Depends how far I get, but we'll see. We may see one later. So in R, it's very simple. If I give you an interval, there's not much discussion about what the center of an interval is, right? It's the midpoint of the interval, right? Any sensible center is going to be that, right? But immediately when you get into 2 dimensions, it's not clear what the center of a set is. And we'll see there's lots of different definitions of it, okay? So what this says is actually super interesting. It says that Y is log-concave, and that says that if I fix a minimum yield, like you say, we cannot economically manufacture this product unless the yield is bigger than 85%. Then it says this is a yield region and it's convex. Could be empty, which would be too bad for you, but it is convex, right? And the reason is this is log-concave, right? So if I exponentiate both sides, or take a log, I get log y is bigger than log alpha. Log y is concave. This is a superlevel set, and a superlevel set of a concave function is convex. Okay? So this is everybody following this, right? So this is actually kind of close to an actual application that's like incredibly useful, which should be kind of obvious. Okay. And the last generalization we're going to look at is convexity with respect to a generalized inequality, right? So here it is. Here I have a function that maps Rn not into R, but into Rm. So it's vector valued. So you give it x and it produces a vector, okay? We say that this function is k-convex. K is a cone, a proper cone. And we say that that's true if Jensen's inequality holds, except that the left and right-hand sides, they're all vectors, right? And the inequality is the inequality induced by this cone, right? So most famous example is with symmetric matrices, right? So if I have a mapping from symmetric matrices to symmetric matrices, here's an example. f of capital X is x squared. X is a symmetric matrix, and the function is I square it. Okay? Then, by the way, you'd kind of guess, it sure sounds convex, right? Because it's like, it's the, whatever, it's the square, and you know that in a scalar case x is. And in this case, that guess turns out to be true. What you'd have to show is the following. It says, what you'd want to show is if I take two symmetric matrices, right? If I then form a mixture of them, so theta x plus, 1 minus theta y, that's a new symmetric matrix. If I square that, that's less than or equal to theta x squared plus 1 minus theta y squared. What does that mean? That means that this inequality here holds for all z, right? So this is what this means, right? So if this holds for all z, and let me ask you, we could look at this. This does hold for all z because these are all now these are simply convex functions, right? And this thing is a convex function here of x, right? So that requires a tricky reading there, but it is. Okay. So this is the idea. You do, like with all generalizations, you want to be on your toes because not everything you think is true. I think one is a famous one is maybe I think it's the exponential of a symmetric matrix. That sure sounds convex. I think it's not. I could be wrong on that. That just came out, and maybe I'm wrong. But if it's not x, it's something like that where it sure sounds like it ought to be true, right? And it just turns out it's not. That one might be actually. I can't remember what is a simple example that violates that. But, okay, so that wraps up actually all the sort of analysis you need to know for the course. What I would actually recommend doing is every now and then, give yourself a half an hour and go back to chapters either 1, 2, or 3 and just reread part of it. What's going to happen is something that made absolutely no sense whatsoever to you maybe 2 weeks ago, it's going to start making sense. I mean, for one thing, it'll be the 4th time you've seen it or something like that, but also it's going to connect to other stuff. So this would be my strong recommendation would be to do something like that. So, okay. So now we're starting on problems, which is not analysis. And of course, the underlying point of all of this is, the following. Convex optimization problems are tractable, right? Basically, we can solve them. That's the point, right? So it's not a question of math when you say, oh, that problem is convex. And I mean, sure, it allows you to make certain assertions about, here are the optimality conditions. I mean, whatever, right? The most important part about it is you can actually solve it. Now that will segue to in maybe 3 or 4 weeks or something like that. But that's what makes everything you just did in the last 2 weeks actionable, right? So that's going to be the point. Okay, so what we're going to do now is we're going to march through what convex optimization problems are. We already sort of introduced this very informally on day 1, but now we're going to do it more carefully. Okay, so first of all, let's talk about what is an optimization problem. Okay, so I actually think of it as an object, literally, in the computer science sense. It has attributes, like it has an attribute which is like, say, this is the objective, and the objective is to minimize f0 of x. f0 of x is a function. Okay? So, by the way, minimize is not a key word in mathematics. It is not. Min is, and it only means and can only mean one thing, which is the minimum of a finite set of numbers, period. That's the only definition of min that's in math, right? Min and minimize are not the same, right? So if you get when I get lazy and I don't want to write out minimize, like on the board, I'll write min, but I'll put a period there at the end, right? So which means, if I don't, then you should, like, I don't know, call me on it or something, right? Okay, so we minimize an objective function here, subject to, and we have inequality constraints and equality constraints. Now for simplicity, we're going to call this the standard form. In the standard form, you're minimizing something, right? you could easily maximize something. And there's whole fields where everything they do is they maximize. Like in economics, that's what you maximize utility or you maximize profit, right? Or something like that. So there's different fields where, and then all you have to do is minimize minus F0, right? As a question.
Does the inequality always have to be like less than equal, like an upper bound? Or
Yeah, so that's a great question. This is just to make it standard form. This says the question is, does it always have to be less than or equal to? It can be bigger than or equal to, right? Suppose you wanted to impose the constraint that f1 of x is bigger than or equal to 0. What you'd do is you'd write that as minus f of x is less than or equal to 0, right? So there are a lot of, and we're going to be talking a lot about these little transformations that you can do to map things into this form. Actually, a whole bunch of them are going to be done automatically for you. In some cases, right? And we have equality constraints, right? And so this is the idea. The optimal value of this problem. So that this is an object. It's a problem. It's got a bunch of different fields or attributes. It's got its objective. It's got a list of inequality constraints. It's got a list of equality constraints, right? So that's the way I think of an optimization problem. Its optimal value is the following. Inf is essentially the minimum. It's the minimum of the objective value over all points x that are feasible. And to be feasible, it means you have to satisfy these inequalities and all of these equalities, like that, right? So this predicate here says x is feasible, okay? And it says if among all such x's you have the smallest value of the objective, then that value is the optimal value, and that's denoted p star, right? So, by the way, there's a slight subtlety here. That's a star, not an asterisk. Asterisk is reserved for things like conjugates and some other stuff that we'll be doing in a couple of weeks. But here, star means optimal. Okay. Now, this is sort of standard math. If this set is empty, that means there is no x that satisfies these, right? Then by definition, the minimum or the infimum of the empty set is plus infinity. Actually, it's not a bad definition. Well, it doesn't matter. It is the definition, right? So it's the definition, and it kind of everything makes sense then. A bunch of rules you'd imagine work. With that, but that's the standard definition that so if I say p star is infinity for this problem, what it means is there is no x that satisfies the inequality, okay? Now, there's another thing that can happen is you can have p star equals minus infinity. And I'll tell you what that means. What it means is there's a sequence of points. Every single one of them is feasible, and this objective goes down and down and down and gets as small as you like, okay? And that both of these, by the way, are kind of pathologies in a practical sense of the problem, right? So if I walk up to you and say, I need you to solve this problem and it's infeasible, like what does that mean, right? If you say, I want to construct the optimal schedule or something for something in the optimal allocation of resources and it's infeasible, I mean, as a practical matter, it's of no use. I mean, actually, all it really tells you is that I formulated my problem, in a stupid way, right? This is called unbounded below, and that's also a pathology, typically, right? Actually, there's a wonderful name for this in some contexts. In some contexts, in like risk-averse control, this thing is referred to as euphoric breakdown, which is like, I think, great phrase for it, right? Because, let's remember what the semantics of this is. The semantics is we are okay with any x that satisfies these constraints, and we are completely not okay with anything that violates them even slightly. Period, number one. Then among ones that are okay, which means feasible, then we are interested in, we are happier the smaller f0 gets. So if in fact there are feasible points with values, it's basically like, hey, maximize or minimize my cost, which is my negative profit. And you go, yeah, well, I mean, here's a feasible x that gives you, minus 10. And you go, cool, I just made, 10 million bucks, right? And they go, here's another one with minus 20. And you go, 20 million, that's great. Minus 50, anyway, so that's why that's called sometimes euphoric breakdown. But anyway, okay. So this is just, the nomenclature. Okay. So So we could talk about what is what is a point, is it optimal and all that. But first we say that a point is feasible if it's in the domain of the objective and it satisfies the constraints. And we say it's optimal if it simply is feasible and has this optimal value, right? And then capital X opt, that's a set of optimal points, right? Which, by the way, is convex. It's not hard to show, right? So, because it's the sub-level sets of F0, it's the P star sub-level sets of F0 intersect the feasible set, which is convex. So if you followed that, great. If you didn't, that's okay too. Okay? Now we have another concept, which is locally optimal. And locally optimal means very roughly speaking, it says that you're optimal if you in a restricted range around that current point. Okay? And here I'll draw one. It's our last example here. I'll just draw that function. I'll try to get a color that's actually, or a marker that's actually visible. So we have x cubed minus 3x, and that function looks like this. Right? That's minus 1, and that's plus 1. Okay? That's your function. That's x cubed minus 3x. And so the point here is, what's P star for that one? No constraints. Just what is P star? It's minus infinity, right? Because these values go as low as you like. Okay? Then this is a locally optimal point. Because, for example, if I add the constraint that x is between 0.5 and 1.5, if it's within 0.5 of 1, and then I simply ask what's the minimum, that's a locally optimal point. It's optimal for that restricted problem. Okay? So that's locally optimal. Okay. Let's look at a couple of other examples just to sort of explain this. Let's take f of x is 1 over x. The domain is r++, right? So positive things. It just goes down like this, right? And P star is 0, right? Because the infimum of 1 over x, as x gets bigger and bigger, that gets smaller and smaller, it's going towards 0. So P star is 0. There's no optimal point, right? And you're not allowed to say x equals infinity. That's not a valid choice. So there's no optimal point. There's no x for which 1 over x is equal to 0, right? So, okay. How about minus log x, right? That's convex. The domain is, again, r++. And that's also going to be, that's actually unbounded below. Just like here, it's got, something that goes down to 0, right? So, okay. So here, as x gets really big, this gets as negative as you would like, right? Maybe slowly, doesn't matter. It's P star is minus infinity. X log x, that's the negative entropy, and that looks like this. That looks like this. That's this function here. Looks like that, roughly. Oh, it's got an infinite slope here, so I'll make it like that. It's got infinite slope right here. By the way, you can either define the value at 0 to be 0, which kind of is what it would be by continuity, right? Where the expression x log x doesn't quite make sense there, right? I mean, but you could, whatever, just by continuity, you could make it 0 there. And that's what people do. So that's a good, this one is what we would, it has no pathologies, right? It's got a single minimum. It's right there. And that value is like, okay, at 1 over e. There you go. That is the minimum value of the negative entropy, or maximizes this entropy function, right? So, okay. So this is just to give you the nomenclature of optimization problems. Okay. A few more things. Yeah.
What?
Yeah.
So why is there, like in the last example, you can say that there's like before it break down the P star negative infinity, but then in the first example, you can't say the same.
Because this is not unbounded below. Unbounded below means that the objective values get as negative as you like. These things, they go down, but they only go down to 0. So You don't get the euphoria kicks in at around -10 in my experience. -100 feels great, but I'm just joking, of course. So okay, fine. Good. Yeah.
The first example is feasible, it just has no optimal.
Yeah, the first example, all of these problems are feasible, right? So I could write down, and we could write down an infeasible.
Why is the second one considered feasible, even if it's unbounded below?
This one. Oh, well, actually, those are actually those two pathologies are at the opposite. They're sort of the opposites, right? Infeasible means there's no x that even satisfies your constraint, so let's not even talk about the objective, right? That's infeasible. Unbounded below is, there's a lot of x's that satisfy your constraints. Not only that, among them, f0 can be as negative as you like. So they are both pathologies, but to me they're sort of at the opposite ends. They're the different thing. Yes.
Is there a term for the first x that reaches 0?
By reaches 0, what's that?
I guess they never do actually reach 0.
You mean up here?
Yeah.
For example.
Yeah. If it's
yeah.
the optimal point.
Yeah. Let's see. I can let's do another example. Let me add a constraint to this one. I'll add the constraint that x is less than or equal to 3. No, okay, sorry, which I will write this way. There we go. All right, I think that was your question about whether yeah. So I'll write x minus 3 less than 0, right? So I'm going to add that. I want you to minimize. Here, watch. I'm going to be good. I'm going to write minimize out. Minimize 1 over x. Then this is subject to this. Okay. Oh, by the way, for us, this thing has a domain which is equal to all positive numbers, right? So, okay. So let's talk about that problem. Is it feasible? It is. There are points which are in the domain of f0, right? Which are less than or equal to 3. Here's a good example. Ready? 1. X equals 1. Okay? So it's feasible. Doesn't have an optimal value. I mean, what's its optimal value?
1/3.
It's 1/3. Does it have an optimal point or multiple optimal points? Name me an optimal point. X equals 3. Are there any others? No. Right, exactly. So in this case, this set x opt is a singleton, and you would say it has a unique solution, which is x equals 3. So this would be, that's a well-posed problem. I mean, it's a silly one, but it's a well-posed problem. Okay. Okay. So there's a concept of implicit versus explicit constraints, and these are actually going to be rather important in practice. So here's what they are. So when I have a standard form problem, right, I've got my objective function f0, I've got my inequality constraints fi, and I have my equality constraint functions hi. Okay, so the first thing is we can't even talk about an x if it's not in the domain of all those functions. It just doesn't even make sense. This is, by the way, worse than being infeasible. Infeasible is like, hey, try this. And you go, sorry, that doesn't satisfy the third inequality, right? That's infeasible. But this is, thanks for proposing an x. I can't even evaluate the objective on it, or I can't even evaluate the third constraint, right? So now a lot of people don't distinguish between sort of being out of domain and being plus infinity, which kind of we'll get to that, but it's fine. Okay, so this is referred to as an implicit constraint, right? That here's an example here, right? There's an implicit constraint that x is positive. The reason is this has a domain which is r++. And so that's an implicit constraint. Simply writing it down, right? You write down log of z, and there's an implicit constraint that z is positive, period. Okay? So, in this class, right? If you're taking a class on complex analysis, z could be negative, right? But the social contract in this class where we focus on convexity, is log has a domain of r++. Same for 1 over x, by the way. Right, so, okay. All right, so these are implicit, sorry. And this is called the domain of the problem, right? And so if you propose an x that's outside the domain, it just doesn't even make sense. I mean, not only should whoever is evaluating the x give you they should give you a really nasty message back, which is like, your choice was so bad, I couldn't even evaluate the objective or constraints to see. So, and basically you should be put on warning at that point, and if you do it 2 more times, you're out. You're barred from it, right? It would be as if the problem, if the variable was like a positive definite matrix that represents, let's say, a covariance matrix. And you go, well, how about this? And I give you a non-symmetric matrix with like negative and complex eigenvalues. Then you're like, hello? Like what? Like, I can't evaluate the log likelihood of that because it's not a covariance matrix. It doesn't make any sense. Anyway, that's what this is. Okay. Now, we'll say a problem is unconstrained if you just have no inequalities or whatever, right? So here's an example. This is an unconstrained problem. The reason is there is a constraint, which is AI transpose x is less than b, but that's built into the log. Because in this course, you take the log of something, it's positive, period. We don't even define it otherwise, right? So that's what that is. That's an example. Okay. Here's another one we'll talk about later. It's called a feasibility problem. Sometimes people write it this way. It says, find an x that satisfies a bunch of constraints. So this says you only have, oh, by the way, some people call it constraints hard constraints because basically they are utterly and completely non-negotiable, right? You violate them, we have no interest in that. If you satisfy them, we don't care if you satisfy them just barely or by a big margin, we don't care, okay? So those are called hard constraints. And so this is just a feasibility problem. And it says, yeah, please just see, can you find an x that satisfies this, right? Okay. And I think some people have a whole, quasi theory of optimization problems, and they refer to this as like, I think one name is a satisficing problem. I mean, frankly, I find it profoundly stupid. And if you understand any of this stuff, it's completely standard and straightforward how to solve. Anyway, fine. So that's a feasibility problem. Then you can write it as a special case of our general problem. What you do is you introduce an objective function which is just 0, no matter what, and has domain everything. This is really dumb, but it does the trick, right? So if I say minimize 0, what I'm really saying is I have 0 affect. I just don't, well, at least on the objective, I don't care. Like any x you propose, they're all, as far as the objective is concerned, they're all the same. And so here you have the constraints. And so for this problem, p star is 0 if there is a feasible point. If there's a point that satisfies it, and then that's actually means it's optimal too, right? And p star is just infinity if the constraints are infeasible. So we'll see that. So-called feasibility problems are the same as our master problems. So they're just the same thing. I mean, they're kind of boring. They only take the values 0 or infinity, but that's it. Okay, make sense? Right. So, and by the way, this comes up in a whole lot of things. It will come up, for example, in economics. It will be this would be the absence of arbitrage, right? And so that'll work this way. X is something you can do, like buy a bunch of these instruments and some bonds over there and some derivatives and some other things. So, that's some portfolio you would construct. And then what these state is that no matter what happens, you will actually not lose money. And in at least one case, you'll make money, right? That's a feasibility problem. And then if it's feasible, you would say you have there's arbitrage in that market, right? And so we'll get to that later, but I just thought I'd just mention that feasibility problems actually, that are literally feasibility problems, are actually, they're going to come up in real applications. Is that?
They're both the same exact same thing, right?
I'm sorry, I missed that. What was that?
Just to clarify, they're both saying the exact same thing, right?
They are saying exactly the same thing. Some people write it this way. I mean, that's the normal way you would talk, if you were talking to a normal person, you might say that. I mean, this just maps it into our standard form. Right. Was there another question? somewhere over there. Okay. All right. So that's a feasibility problem. And finally, now we get to a convex optimization problem, right? So, and here it is. It is this. It's a standard form problem where we restrict the curvature of the functions. That's all it is. And it's this. The objective that we minimize has to be convex. The constraints, which we are, in this case, upper bounding by 0, have to be convex functions. And the equality constraints have to be affine, or what people call them linear equality constraints. So these are the rules. So roughly speaking, it says objective has non-negative curvature. Constraints all have non-negative curvature, and equality constraints all have 0 curvature, which is affine. Make sense? Yeah.
Why do the equality constraints need to be affine? And not convex?
Why? It's a loaded question because this is the definition of a convex optimization problem. So morally speaking, I think I can answer it this way. I'm allowed to say because that's the definition. Okay. So, but I mean that's kind of obnoxious. But we'll see actually that if we'll get to some interesting examples where these constraints are when you have an equality constraint that's not. Let's see. Well, by definition, you don't have a convex problem. And in fact, a bunch of our methods won't work on this. Now, sometimes we actually can solve problems like that. So, sorry, that was a long and weird answer. Okay, I'm going to revise my answer. It's this. It's because this is the definition. How about that? But I won't say it in the obnoxious way. So, okay. Okay. So, and these equality constraints, we will often collect them and write them as just in a single matrix form, AX equals B. Okay? So, okay. Okay, so let's look at an example. It looks like this. Oh, and by the way, let me point something out here, very important. So a convex optimization problem, we refer to its representation through its objective function, its inequality functions, and its equality constraint functions, right? So it's, we'll talk shortly about the idea of an equivalent problem, but now it's actually literally it is, when you have a problem, it has attributes which are the objective and things like that, and that's what, to be the attribute of being convex depends on how you describe the problem. We'll get to that in a minute. In fact, this is an example of that. So here's a problem. It's got two variables. I would like to minimize x1 squared plus x2 squared. Well, that's just the sum of the squares, and that's like a nice bowl that kind of goes up like, you know what it looks like, right? And you have some constraints. You have f1 of x is x1 over 1 plus x2 squared is less than or equal to 0. Well, you can ask yourself, is x1 over 1 plus x2 squared convex? And the answer would be it's not. Okay? So this thing is not a convex problem. Okay? And the last constraint is that h, so I think you asked a question about why does it have to be affine, and I said, well, it's the definition. Here's an example where h of x is for sure not affine, right? It says that x1 plus x2 squared has to be 0. Okay? So this problem fails. And, we can even walk through the code. If I took this problem and I called it myprob, and I called the myprob.isConvex method on it, then here we will walk through what the code does. What it does like this is it says myproblem.objective, that's going to be f0. I call the .isConvex method on it. And in this case, that would evaluate to what? True. It's true. Okay? No problem. Now, the second part of implementing the isConvex method on a problem is to iterate over the inequality constraints. And you'd say for inequality in inequalities, you would say myprob.inequality of I. I'm just saying, rough pseudocode here. .isConvex. Well, there's only one in that list, and it would return this function, and that would evaluate to what? False. At that point, it's game over. But if you wanted to be really sure it was over, you would actually go to the equality constraints, and it would have it would actually do, it'd be for equality constraints for equality constraint inequality constraints, equality, my prob dot equality constraint function of 0, I'm using 0 indexing, dot is affine, and it would evaluate to false. Everybody got this? Okay. Now, it's silly because you look at this and you're like, well, this is dumb, right? I mean, this thing is the same as x1 just being less than or equal to 0. And the square of x1 plus x2 is 0. That only happens if, so basically you can rewrite the problem this way. Okay. Now what we do is we would call this problem and this problem equivalent problems. What that means is if you can solve one, there's an easy way to solve the other. We'll talk more about that. But if you've taken a course in computer science, like almost any, this is the standard idea of a reduction, right? We're not going to make it fancy and have polynomial reduction and all that kind of stuff. But the point is, for us, it's going to be informal. It just means two problems are equivalent. If when I solve one, I know how to solve the other. And if I can solve the other, I know how to solve the original one. Okay? So these are equivalent. They are not the same. Let's walk through the implementation. This is my prob, and this is my alternative prob. Okay? So let's walk through the equals method between two problems. And the way that works is this. It takes here's an implementation. This is what it means to be equal. It says, are your objectives equal? And that would evaluate to what in this case? True. Okay? Then it goes like this. It's really dumb. It says loop over the constraints and just check if each constraint function in the two problems are the same. That would evaluate here to false, right? So these are not the same problem, but they are equivalent. Okay? So, I mean, this is not a big deal and it should be kept informal, but it's also an important idea. Okay? So this problem is not convex. This is convex. And this tells you that, yes, a non-convex problem can be equivalent to a convex problem. And that's very confusing, but too bad, right? So, okay. Yeah.
Be the same as just saying the P star that solves this problem is the same as the P star that will solve that problem? Would that be another way to check equivalency?
Yes, no, not quite, right? Because when you say they're equivalent, it actually doesn't really, it means that you have a very simple method. It says that once you solve that, I have a simple method to solve that. And that simple method is, well, it's very simple. I take a solution of this, which we could figure out like real quickly, but I'm not going to. But we take a solution of that, actually the solution of it, because it's going to be unique. We take the solution of that, this thing, right? And then actually you just simply put it over there. It's the same x1 and x2. We'll see other cases where you might have to do, when two problems are equivalent, you might actually have to do a little bit to transform back, right? But it's not the same as just P star being the same. Okay. So now we'll talk about local and global optima, the plural of optimum. Okay. So it turns out any locally optimal point of a convex problem is globally optimal. So, I mean, it's not hard to show. It's I'll draw a picture in just a minute to show you what this means. But it is kind of worthwhile to sit back and say, like, to realize how impressive this is, right? So, and I remember being told like point blank by someone super smart circuit designer. And I said, that's the globally optimal circuit design. And he looked at me and he said, how can you possibly say that? He said, this is a circuit with 45 lengths and widths. What hubris? How could you say that? How do you know someone can't come up with another set of lengths and widths that, anyway, I looked at him and said, well, it's just because of the mathematical features of this problem. That's how I can make this. But it's probably worthwhile for all of us to realize how absurd a statement that sounds like, right? If you solve a problem with, 10,000 variables, and you'd say, I just worked out the minimum fuel trajectory to put your satellite back on orbit where it's supposed to be. Perfectly reasonable person would say, how could you say something like that? There are so many sequences of thruster burns and things like that would get you back. How do you know? How could you possibly know that this has minimum fuel? Do you see what I'm saying? By the way, we will, after this little speech, I quit, and we will get you, and that's all we're going to say from now on. We'll just say, hey, this is that's the optimal thing, and you get used to it. But it is probably worthwhile to think about how strong a statement it is. And it kind of all comes back to this, right? So, okay. And let's see why. I'm just going to draw a picture. In fact, we're not going to follow that. I'm just going to draw a picture. So let's suppose that you have a point here. It's locally optimal. So I'm going to call that x loc, right? But let's suppose it's not globally optimal. So that means I'm going to find another point that's feasible and has a lower objective value. And I'm just going to call that, over here, x tilde, right? It could be x star, an optimal point, right? So this is feasible, locally optimal, and this has an objective value less than that. Everybody got it? Okay, now I do this. I draw the line segment between them, okay? Now, on that line segment, are all those points feasible? Why?
The combination of the two.
Yeah, because x loc is feasible, so is x tilde. The set of feasible points is a convex set. That's a line segment. So any point on here is feasible, okay? Now I want to draw, as I move, let me call my parameter t. So this is t equals 0, t equals 1. And I want to draw the objective value as I go from t equals 0 to t equals 1, okay? And I know 2 points already. I'm going to draw f0 of that point, right? This one, it starts at f of x local, here. It ends at f0 of x tilde. By assumption, that's better than f0. So I don't know where it is, but I'm going to draw it here. That's at f tilde of x, what am I doing? f0 of x tilde. Everybody got this? Okay, now, on this line segment, we know that when I draw that, it's a convex function. Because it's a convex function of t, right? This is restricting a convex function to, in this case, an interval, but a line, right? And it's convex. I have to draw a convex function that starts here and ends here. Everybody got that? Okay, now when I do that, there's lots of ways to do it, but no matter what I do, it has to go down a little bit here. Okay? Okay. Now we got a problem. What is the problem? Remember, somebody alleged that x was locally optimal. So this means whoever said that was a liar. Let me tell you why. It says that there are points on this line segment with really small t, which is, it's very close to x local, and the objective value is less than x local. So x local was definitely not a locally optimal point. Everybody got that? I mean, honestly, I could write it out as a proof. It's actually shorter if I do, but the picture kind of tells you everything. Does that make sense? So that's the idea there. Okay. Okay. Now here we can give like a extremely simple optimality condition for what if f0 is differentiable, right? And it looks like this. It says that a point x is optimal if it's feasible, and the following is true, is that if x is the set of feasible points, it says that the gradient of f transpose y minus x, that's got to be bigger than or equal to 0 for all feasible y. And let's draw the picture. So these dashed curves are the level curves of f0, right? So if you slide this way, you're going downhill and you're getting better values of f0, which by the semantics of that being the objective means you're getting happier. So you're getting happier as you go down this way, right? Okay, so here, but these are the acceptable points. And so to solve the problem visually, it just means you slip down, you find the lowest level curve that is on this thing, and that's going to be this point here. Okay? And what happens there is actually kind of interesting. It just touches it. And the gradient, which would be the outward normal, so the negative gradient like this, points downhill. And that is actually orthogonal to this tangent line here, right? So another way to say it is that the gradient defines a supporting hyperplane to the feasible set. That would use the language we had before. Okay? So that's this. I mean, I think this is it's pretty basic, and weirdly, it looks complicated. Proving both directions is each like one line for each one, because it's just silly. So some things look and sound complicated and fancy, and they're not. This is one of them. Okay? So I think the picture is pretty clear, right? So this is the picture. Okay. Now, we can instantiate that, various versions of it. So here's one version, is suppose there's no constraint set. If there's no constraint set, then what we're saying is x is all of Rn, and this inequality has to hold for all Rn. Any comment about that? If I tell you this inequality holds for any vector y, the only possible way that can happen is this gradient has to vanish. Okay? Because if this gradient didn't vanish, then I would pick y to be minus that gradient multiplied by your favorite extremely large number, right? And then this thing here would definitely not be bigger than or equal to 0. Everybody following that? So that would be the idea there. Okay, so basically this recovers, I guess, what you know from your Calculus 2 or whatever course, right? It says that in an unconstrained problem, if f0 is differentiable, the gradient vanishing is what it means to solve the problem. By the way, this is a bit different from your Calculus 2 course. Let me tell you why. In your Calculus 2 course, when you said the gradient vanished, all it meant was that it's like a stationary point of the function. It could have been a saddle point, it could be a maximum, it could be a local minimum, local maximum, all this kind of stuff. Here, because we also know f0 is convex, it's actually globally optimal, right? And I didn't even have to say the globally. It's just optimal, right? So that's it. So, okay. So what that says is, when in Calculus 2, you were taught how to, do baby optimization stuff, which was kind of a behavioral thing. And it basically said, you take the function, set the gradient equal to 0, and then something happens after that, right? That's my general memory of this. It turns out, for convex functions, that's exactly correct. That is, oh, and not only that, you will get an optimal point, period, right? So, and none of this weird legal boilerplate or footnotes that says, it might be a maximum, might be a minimum, it might be a saddle point, might be a local minimum, might be a local, none of that boilerplate. It's just optimal, period. Okay? So, okay. We'll look at optimality conditions later in the class, but some of them are just very easy to work out directly from this general principle. So if you have an equality constraint problem, what happens is you want to minimize f0 of x subject to ax equals b. And so you're optimal, you have to be feasible, you have to be in the domain, of course, and then you can work out what it means for that gradient inequality to hold for an affine set. And when you do, it's going to end up looking like this. That's also from your Calculus 2 class, because these are Lagrange multipliers. We are going to cover that in about a week and a half, 2 weeks, in a theory called duality, after which I believe you will actually understand it. So, because I don't mind admitting, I saw things about Lagrange multipliers 2 or 3 times and had no idea what they meant, did. Why would you do this? Why would you do that? Why? Anyway, you know what I'm talking about, probably, right? So, unless you're in there are fields where this does come up. If you're in economics, maybe if you're in mechanical engineering, you actually do have a feel for it because it comes up there. Maybe in statistics, I don't know. But the point is, we'll cover this in detail later. So, okay. And you can work out other cases like minimize a convex function over the non-negative ortho, and you can work out what it means. And actually, it's also makes perfect sense, right? So it would mean that if I minimize a convex function over non-negative ortho, let me just draw this. So I want to minimize a convex function over here. And here's an example. Here are some sub-level sets, okay? So like this, right? Like that. Here's some, whoops, okay, these are sub-level sets, right? Like that. So, that's the optimal point, right? And we can sort of check this, right? Because what happens here, and this is just kind of very intuitive, right? What it says is that this in partial partial f0, partial x2, that has to vanish. If it didn't vanish, we'd be in trouble. Because I could slide up and down here in the direction of the negative gradient and actually get a slightly better objective value while staying feasible, in which case it was not optimal, right? But I'm slammed up against the boundary of the constraint here. I would love to go in that direction. I'd love to, because my objective would go down. The problem is I'm at the boundary of the feasible set and I can't, right? So anyway, when you work this out, you can just work this out algebraically and you get something like that condition there. So anyway, we'll come back to optimality conditions in about 2 weeks. Okay. Now we're going to talk about equivalent problems. I already said a little bit about it earlier. We actually saw 2 equivalent problems, in fact, right, earlier. Now we're going to talk about it because it's kind of an official idea we have. So 2 problems, and we're going to make it informal in this class. In CS theory, it's not informal, right? Here it is. There it's called a reduction, by the way, right? So here it's not. It's going to be informal. And we say basically if one problem is equivalent to another, if from a solution of one, I can create a solution of the other, right? And vice versa, right? So that's what that means, right? So that's exactly the idea of a reduction in computer science. Okay. And so there's a whole bunch of them that you should probably know about. And in fact, a lot of the software tools you're going to use, actually you're going to use on your behalf many reductions. And they'll use many equivalences, which are reductions in computer science that you don't need to know about, right? So, but you need to know about some of them because they're actually kind of, and I'll just mention some of them. A lot of them are kind of generic, but let's look at some. So here's one. Here's a problem with equality constraints, and we can just basically eliminate the equality constraints. I can take a new variable, right? And the first thing I do is I find a vector x0 that satisfies ax equals b, and I find a matrix whose range is exactly the null space of A. And what that tells you is that ax is equal to b if and only if you have the form x equals fz plus x0. x0 and f we can compute from A and B, right? So we compute them. I won't go into how we do that. There are lots of ways to do that. So you do that. If you do this, then this problem is equivalent to that problem, right? Oh, by the way, they're not equal at all, right? Like, I mean, for one thing, at a very gross level, it's not. If you say this problem dot equality, if you say what is the length of this problem dot equality constraints, it's going to be however many, let's say this p in a p equality constraints. It'll be p. Here, when I say this second problem dot equality constraints, if I say length of that, it's a list. It's an empty list. And so it's 0. And so end of story. These are not equal, but they are equivalent, right? And here, the transfer, in this case, the p star of the 2 problems, the optimal value is the same, right? And to explain what you do, you say well, you want to solve this. So what we do is first we compute this f and the f and the x0. Then we solve this problem. Now, z has nothing to do with this problem at all, right? But then what I simply do is I return, in this problem, I return fz star plus x0. And that's going to be the solution here, right? So this actually also has a very important, like if someone comes up with a super fancy solver for a problem, right? They go, it's awesome, right? It's super fast. I don't know, whatever it is, doesn't matter, right? Then you'd say, only minor problem? It doesn't support equality constraints. Everybody got that? So this actually now, it's like no problem. I just write a wrapper around it. And my wrapper takes problems like this, calculates f and x0. We could write the whole wrapper beautifully. Like the first thing you do is you attempt to solve ax equals b. What if b is not in the range of A? What do? I return that your problem is infeasible, period. And then I don't have to do anything else. If it's feasible, I'm going to find an x0 and I'm going to find this f. I'm going to solve this problem using this person's fancy solver. I will then quietly return fz plus x0, and that will in fact be a solution of this problem. Everybody got it? So, okay. So that's called eliminating equality constraints. And actually there's a whole lot of confusion about that. Like I think some very naive people think this is great. And you say, why? And here would be the story. It's naive, it's totally wrong, but here's the story. I mean, it's plausible if you don't know what you're doing. Here it is. They say, well, I have this problem here. X has dimension 100, and I have 50 equality constraints. Everybody got that? Now, down here, that's assuming that's like it's got full rank and all that. So down here, Z has rank 50. Dimension 50, right? Because if I have 100 dimensional space, I have 50 equality constraints, everything's full rank, Z is going to have dimension 50. And then someone says, oh, that's a better problem than that one to solve. And you go, why? And they go, hello, wouldn't you rather solve a problem with 50 variables than 100? Everybody see what I'm saying? It sounds plausible, but it's completely and totally wrong, which you will know later. So in fact, it could be the exact opposite, that you would much rather solve a problem with 100 variables than 50. I'm getting ahead of myself, but we'll come back to that later in the class. Okay, so, okay. You can do the opposite, yes?
How do you actually compute x naught f?
That's linear algebra. Yeah, that's just standard linear algebra, right? I don't know. I do a QR factorization of like f, or I don't know, something like that. A. Is that? I mean, I'd be happy to tell you later or something, but that's just linear algebra, right? Okay. Next up is the opposite of eliminating equality constraints, is introducing equality constraints, right? Weirdly, this sounds really dumb. It's unbelievably useful, and we will see that later. So how does that work, right? You start with a problem like that, and you introduce a new variable, and you introduce equality constraints, right? Now, what's hilarious about this is someone says, oh, thanks for your problem. I just made you an equivalent problem. Oh, and by the way, you have to check that these equivalences play nice with convexity. I didn't do that for the other one, so let's go back and look, okay? So here, if that's a convex problem, we have to check this is. How come this is? How come? Yeah, because this function is convex because it's a convex function precomposed with an affine function. These are convex for the same reason. So we do have to say that. At this point, we're not even saying it, right? So, okay. Okay, so you uneliminate here. Now, what's hilarious about this is someone says, oh yeah, I just converted your problem to a new problem. You go, oh, thank you. That's great. Tell me about the new problem. And you go, well, it's got more variables. And you're like, okay. And you go, oh, by the way, your problem didn't have any equality constraints. Now you have a bunch of them. This doesn't sound good, right? This story doesn't sound like it's going. Anyway, believe it or not, it's going to be super useful, this idea. Okay, so here's one. You can, this is a famous one. These are all methods that a lot of people know and would learn about by hand, actually literally since the 1940s. Okay, so here's one. You don't want to, you can take a linear inequality and introduce what's called a slack variable. That's like a standard term, not in math, but in, for example, OR, so or in optimization, right? And what I mean, and these are just very simple and dumb, these little transformations, but this one says, we rewrite this as AI transpose X plus SI equals BI, where SI is a number bigger than 0, and that's called the slack. Right? And slack makes perfect sense, right? So it means if you're right up against it, S is 0. If S is positive, it means this constraint is satisfied with strict inequality, right? And slack comes from the idea of like a chain or a rope between two things, right? The constraint is if I put a steel cable between two things and I make it a meter long, then those two things cannot be more than a meter apart, right? If they're exactly a meter apart, then that chain is taut. That's not a word in optimization. But if they're less than a meter apart, then the chain is not taut. There's zero tension in the chain, and then it's slack. And that word did make it into optimization. Everybody, so that if you're curious, that's what it means, right? Slack rope or slack cable or something. Okay. Okay. So this is called introducing slack variables. We'll show a couple of, this one is also kind of interesting. This says, I have my standard form problem and I can rewrite it this way, which is hilarious. I introduce a new variable. So now my variables are xt. Now when you hear xt, you should be thinking graph, epigraph, hypergraph, these kinds of things, because that's what it generally means when you have a variable and a comma, a scalar, right? And so here, this constraint here simply says that xt, the pair xt is in the epigraph. I mean, it's kind of silly. This just says t is bigger than the objective, right? And then it says you minimize t subject to this, okay? Now, here's what's cool about this. Some people say this in a very fancy way. They say things like, for convex optimization, a linear objective is universal. I don't even know what that means. Anyway, but so it says, without loss of generality, you have to, if you can handle this constraint, and then you have a linear objective, you're good to go. You just solve the problem in epigraph form. Okay, make sense, right? So that's why a lot of times if you'd say, you'd say, oh, I went to Google, I looked for code to solve this thing, and it's not there because it's what you see. The only thing I can find can solve a linear objective, and my problem has like a non-linear objective. And the reason is people are just expecting you to put something into epigraph form. Okay, so okay. Other things you can do are things like selective minimization. So you have two variables here. I could actually eliminate x2. Suppose I can analytically minimize over f0 over x2, right? Then I can do that, and I have a problem that looks like this. This would be the case, for example, if this function were quadratic in x2. I can minimize a quadratic analytically. I could do that, and then I eliminate x2. And this is basically part of dynamic programming, right? That's what would happen in dynamic programming. If you want to find a good choice of an input over some sequence, you start at the end, you minimize over the last one, and then this function is called like the value function or something like that, right? And you just keep going, and it all works. And this one also, like all of these play nice with convexity. So here, the reason f0 tilde is convex is because it is partial minimization of f0 with respect to the variable x2. Okay? Everybody got that? So all the rules you saw before we're now using for problems. Okay. I'll say a little bit about quasi-convex optimization. So if I have convex inequality constraints, linear equality constraints, and I minimize a quasi-convex function, that's called quasi-convex optimization. And you have to be very careful here because, for example, this is for sure a quasi-convex function. And by the way, it's actually really flat here. Like it's not that it's visually flat, it's flat in this one. And then it keeps going up. This is quasi-convex, okay? That point is for sure locally optimal, right? Because you wiggle a little bit left and right and the objective does not go down, right? So, but it is clearly not the optimum, which is here, right? So some things don't hold in this case. But it turns out we can solve these using convex optimization pretty easily. And I'll show this trick and then we'll quit for today. So if f0 is quasi-convex, then what you do is you find a parameterized set of convex functions which have the following form. This defines a convex set in X for each t. That's actually what it means to be quasi-convex, right? And so what I do is I express that as a convex function phi t being less than 0. And here's an example. The ratio of a convex to a concave positive, a non-negative convex divided by a concave positive function, this is actually quasi-convex, okay? How do I check that? Well, I want to know what happens if p of x, I want to look at the sublevel set, which is p of x over q of x is less than or equal to t. Q is positive, I multiplied on the other side, and I got p of x is less than t q of x. Everybody following this, right? I pull it over and I get p minus t q of x. If this is less than or equal to 0, then this thing is less than t. Okay? So that's a convex function. So it's a convex in x, not jointly in x and t, but in x. For each t, positive, non-negative, this is a convex function, right? And so it says, so what this says is I have a specific way of seeing if I can find a point that has that value. And then what we do is just bisection. And I'll quit very briefly, but this is the idea. What you do is you simply solve a feasibility problem. This one basically says, can you find a point where f0 of x is less than t? That's this, right? These are the constraints. If you can, then you found a point, and then you know for sure the optimal p star is less than that number. If the answer is you can't, then you know that p star is above there, okay? And you just use bisection. So we'll quit here today, and then we'll continue on Thursday.